Hi guys, welcome back. Let's see. I don't know if this is going to work. This is an experiment, of course, and I have very little confidence in my ability to carry this off, but we'll see how it all goes. Okay, I'm going to try making a video about the first section of chapter 5, which is, gee, my iPad is talking back to me. Okay. Which is about the trapezoid rule. Chapter 5 is about, let me back up. Chapter 5 is about numeric integration and differentiation. And oddly enough, in numeric analysis, integration is easier than differentiation. Go figure. I'll explain why later. But that's why the chapter is starting off with numeric integration, because it's actually easier than differentiation. And now you probably learned the trapezoid rule when you were studying calculus. I'll just briefly review it. Remember, a trapezoid is a quadrilateral in which two opposite sides are parallel. And the area for a trapezoid is very simple. It's equal to the average of the two lengths of the parallel sides times the distance between the parallel sides. So the way I've drawn it here, we could say we've got two different widths, a lower width and an upper width, and we take the average of those two widths and multiply by the height. However, when you think of it, applying it to Riemann integrals, we're going to divide up an area under a curve y equals f of x. We're going to divide it up into small vertical slices. Each vertical slice is approximately a trapezoid. In this case, it's the vertical sides that are parallel, and the distance between them is this increment h, right, between points of the mesh. So h is the distance from one of these mesh points to the next, and the slice of the area is not exactly a trapezoid, but it's pretty close. It's got two parallel sides, and if the distance h is pretty small, then the upper side will not exactly be straight, right? That side will not exactly be straight, but it'll be close enough that the trapezoid formula should give us a pretty good value for the area. So what we do is we add up the areas of all these trapezoids, or approximate trapezoids, in order to approximate the area of the integral. Now, in what follows, note that n is equal to the number of interior mesh points, right? So that's the point starting from a plus h and ending with a plus nh, not including the extreme endpoints a and b. So if we want to well, estimate the area under the curve between a and b, that means we're computing an integral and trying to estimate or approximate the value of an integral from a to b of f of x dx. Oh, I left off the dx. Oops, what have I done? Okay, take two. If we want calculating the area under the curve, or estimating the area under the curve, that means estimating or approximating the value of the integral from a to b of f of x dx. And if we add up all of those, all of the trapezoidal areas, right, to get an approximation, then we're at each I, we're going to add up the let's see, the height of f at the left endpoint, the height of f at the right endpoint, divide by 2 to get the average, and then multiply by the width, which is h. So here we have the average height between those 2 points. That is the height at a plus ih and the height at a plus I plus 1h. And then, of course, we multiply by the width of that trapezoid to get the area. Now, it's worth pointing out that when you add all this stuff up, what you end up doing is each of the values of f at each one of these points here, for example, here, f of a plus ih, each one of these values ends up being counted twice. It gets counted once when it's the right endpoint of the interval, and it gets counted a second time when it's the left endpoint of the following interval. So therefore, another way to write this would be to say we just add up all these values and don't divide by 2, because each one of them gets counted twice. So add up all the values of f at all those interior mesh points. The only points at which well, the only points which f is not counted twice are the extreme left endpoint at A and the extreme right endpoint at B. So for those, we just divide by 2 and add them up. But for all the others, we simply add up the values of the points at all those interior sample points. So if you look at the formula this way, you could say that what we're doing is we're just sampling the function f at endpoints in the middle and then at the 2 endpoints. And then we use those to basically just add up all those sample points and multiply by h to get our value for the, or estimate for the area. Now, what we're going to want to do is we're going to want to observe what happens as the number of these intervals, of these trapezoids, doubles. As you'd expect, the more trapezoids you have, the better your approximation of the actual value of the integral. But what's interesting is to observe exactly what the behavior is. And the clearest way to do it and the easiest way to calculate it is to see what happens as you double n, the number of trapezoids. Of course, when you double the number of trapezoids, you're going to cut the width between the trapezoid, the distance between the trapezoids in half. So we're going to double n and we're going to halve h, right? Okay, I have some, here I have some algebra worked out to show the difference, but I think maybe it's easier just to look at the picture at the bottom left down here. What you can see is that the orange, no, I'm sorry, the blue, let me start with the blue sample points. The blue sample points represent what happened on the previous iteration, in other words, when before we doubled n. So those represent the sample points before n was doubled. When n is doubled, then we still have those points that we're going to want to sample. But in addition to those points, we also get points halfway between each one of the blue points. So in doubling the number of trapezoids, we get to keep all our old sample points and we just add in new sample points in between all the old ones, right? So computationally, this is a very efficient way of doing things. We don't have to start from scratch at each time we double n. We simply add in new sample points in between the old ones. And this is the way the author's program works. So let me try to explain that. So what he does here is he had a function, a MATLAB function called trapezoidal. I modified it just slightly so that it would take function handles as an input. So my version is trapezoidal_f, trapezoidal f, and that'll be up on the Canvas module for chapter 5. And it takes 4 inputs. The first 2 are the endpoints, the left endpoint A, the right endpoint B. Now, what this thing is going to do is it's going to not only calculate the or estimate the area using the trapezoidal rule, but it's going to do it for increasing numbers of trapezoids. So as the number n of trapezoids increases, in fact, successively doubles. So the third input you have to give the function is the initial number of trapezoids, n0. And then at each iteration, well, it'll start with n0 trapezoids, and then it'll double it each time. And so eventually it's going to compute the integral for n0 trapezoids, for 2n0, for 4n0, all the way up to 256 n0 trapezoids. So I believe that's going to be 9 different estimates it's going to give you, and then we'll be able to see how the approximation changes as n increases. Okay, here he's just initializing the outputs. He's going to return the values of the integral for each value of n, also the difference between those values, and the ratio of the differences, right? And he just initializes those as 0 column vectors, right? So each one of these is a column vector with 9 entries in it, 1 for each of the iterations, right? Each of the values of n. One slightly irritating thing here is that the strategy in doing this, as I said, is that we can always reuse the work we did for the previous n in order to get the next n when n is doubled, right? We keep the values of, that we'd already used for n, and we can reuse them at 2n. The only time this doesn't work is initially when we do n0. N0, when we start working on this, we have nothing done, right? We haven't done any earlier calculations. So what he does is he actually initializes things for the case when, actually down here, he initializes things for the case when, for n0 when we start. So let me explain. He's got two variables here. He's got sum end, which is simply the value of the function at a over 2 plus the value of function of b over 2. And right, those are the half values at the endpoints. We always need those. Whatever n is, we're always going to use those. What's going to vary as n changes is the sum. And this variable, the sum, it represents the sum of the interior points. So the sum here corresponds to this term over here. It's the sum at all of the interior points. Sorry, not the last one, but just the interior points at the in the interval, not at a and b, but just in the interior. And then the idea is that he can use the sum from the previous value of n for the next value of n. He just needs to throw in the new values at the points halfway between the old mesh points. So what he has to do, though, for n0 is he has to say, well, for example, suppose you say n0 is 4. So you want to start off with 4 trapezoids. What it will do is it'll initialize the value of the sum for what would be the case if we did it for 2 trapezoids, right? Because that would have been the previous case, right? The previous case would have been 2 trapezoids, which would then be doubled to get 4. So he actually does the calculation as if there were 2 trapezoids, and he uses that to initialize the sum. And then he can just go into the loop where we feed in the previous sum into the next iteration of the loop and get the updated sum. So here's the main loop. This is where most of the work really does. And it's just a couple of lines, as you can see. It's like 7 lines of code, 8 lines of code. So I is equal to the power of 2, right? In other words, I governs how many trapezoids there are. In fact, the number of these trapezoids or sample points is 2 to the I times n0. Right? I goes from 1 to 9, but he actually then subtracts I from 1 when he sets n. So it actually starts off being n0. H is the width of the entire interval from a to b divided by n, so b minus a over n. And remember, we're assuming that at every step of the way here, we already have the sum for the previous number of trapezoids, half as many trapezoids. So we'll simply begin with that sum, and we'll add in the new trapezoids. These are going to be the new ones. These are going to be odd points, right? If you like. The orange points, which are the new ones, they're going to be points that are halfway between the old points, and they're going to correspond to points when the index is odd. So for example, this is when I equals 1, this will be when I equals 3, this will be when I equals 5 and 7 and 9 and so on, right? And of course, we don't need the ones when I is even because they are included in the previous iteration, in the previous sum. So he has the loop, or the for loop go in increments of 2 here, right? So he starts at 1, it goes in increments of 2, so he's just picking up the odd values. Okay, good. And then finally, when he's added those all up through all the n, then he sets the integral for the current I value equal to h times the values at the endpoints, which were sum n, and the current value of the sum at the interior points, right? And he's going to do that for each value of I to create this vector. Finally, when he's got when he's gone through all the I values, and he's got all the different estimates for the integral, for all the different values of n, then he's going to calculate the differences between those integrals and the ratios between the differences. And this is actually quite easy to do in MATLAB. You don't need a for loop or anything to do it for multiple values. You just do component-wise vector operations. So for example, the difference vector is supposed to record the difference between successive approximations of the integrals. So for example, if you have, if you know, your integral vector is going to look like this. It's going to have a value for the first integral for the first value of n, and for the second value of n, and so on. So you're going to have all these different I values in this integral, in this vector. And then what you want to do is you want to subtract it from itself, but in a slanted way. That is, you want to take the value I2 and subtract the value at I1. And you want to take the value at I3 and subtract the value at I2, and the value at I4 and subtract the value at I3. Right? So this is actually quite easy to do in MATLAB. You just say it's, you take the integral from 2 to 9, starting at entry 2 up to entry 9, and you subtract the integral vector in positions 1 through 8. So the leading entry in the first term here is going to be the second entry of the integral vector, and we're going to subtract off the first entry of the integral vector. So what we'll end up with is a vector with 8 entries in it that'll have the differences. Okay, so here's my MATLAB. I've got the trapezoidal f function here, and what I'll do is, let's see. Oh yeah. First of all, let me just do this. I'm gonna enter format long so I can see the numbers in